Previously, we were able to calculate the change in enthalpy of a reaction by doing the following. We said that the delta H for a reaction is equal to the sum of the delta H's of formation of products minus the sum of the delta H's of formation of the reactants. Products minus reactants. We said if this was negative, the reaction was exothermic; positive, it was endothermic. So we know how to calculate the change in enthalpy for a reaction. Remember that enthalpy cannot be measured directly. You measure the change in enthalpy. Enthalpy is a measure of the energy content of the system at constant pressure. Today we're going to calculate delta H of a reaction slightly differently. If you don't know the delta H's of formation, you can calculate delta H differently because enthalpy is a state function. It depends only on the beginning and the end. So when the bell rings today, unlike most days, you're going to go to 7th hour. Your initial point is 5th hour. Your final point is 7th hour. The path you take is irrelevant, so it doesn't matter if you stop at the restroom, go to your locker, go make out with your girlfriend, etc. It only depends on where you start and where you finish. If the delta H's of formation are not known, you can do something a little bit differently. If the reactions can be summed to a net reaction, Hess's law says that the enthalpy of the reaction is the sum of the enthalpies of the combined reactions. Because this is a longer period, we can come back and watch this video if you wish. He also goes into great detail determining Hess's law. I'm going to do it my way initially because I have a very simple approach to doing it, but that way may be helpful to some of you as well.
So since we're going to be so ahead, are we going to have like a free day?
Free day? What's a free day?
I don't know a free day.
I don't know what a free day is. Can we discuss this at the end? All right. For example, let's say you want to go from A to Z, but you don't know the delta H of formation of A and or Z. So you can't do Z minus A like we did previously. Instead, we're going to do it in 2 steps. For example, if I wanted to get to the back of the room very quickly, if I were 20 years old, I may decide I wanted to leap the desk and run straight back. And since I'm not 20 anymore, I'm 21, I don't feel like doing that. I'd have to go around, and then I'd have to stop and go back. So I'm doing it in 2 parts now, with my midpoint being M. If the sum of these 2 reactions is equal to the net equation of A to Z, then the delta H for that A to Z reaction is the sum of these 2 delta H's. That is delta H1 plus 2. That's Hess's law. If the equations, when summed together, equal the net, the delta H of the reaction is the sum of the individual delta H's. There can be many more than 2 reactions. I can't imagine you'd have more than 5, but there can be quite a few reactions. And this all works because enthalpy is a state function. This next one we can walk through piece by piece. Can be a little bit tricky. We'll work through it very slowly, but I think this will help you greatly to understand how to implement Hess's law. The way I do it is I look at the net equation. I look at the first reactant, which in this case is A. Now I'm going to look for all the A's. I've got 2 A's here and an A here. And this is very similar to what you might have done in Algebra 1 probably 2 to 4 years ago. For example, if I wanted to sum two equations, x plus 3 equals y plus x plus 4 equals y, the sum of those two equations would be 2x plus 7 equals 2y. Alternatively, if I had x, let's make this 3x plus 4 equals y, and 8 is equal to y plus x. If I wanted to sum these two equations, I've got two of the same on the same side, so that's 1y plus 1y is 2y. 4 plus 8 is 12. Here, because these two variables, which are the same, are on different sides of the equation, we would subtract them. Whichever side has more keeps it on its side. So 3x minus 1x is 2x. All right? Very simple algebra, and you're going to see the same thing here. So if they're on the same side, you add them. If they're on different sides, you subtract them, and whichever side has more keeps it on its side. If, for example, you had like 3x plus 2 equals y, and 6 is equal to 2y minus 3x, let's make that plus 3x, then those would cancel. So if they're on opposite sides with the same coefficient, they cancel. Same side, you add them together, and then you could solve for y if you were so
For
inclined.
setting this up, isn't it, can we just look at it as algebra or something?
It is algebraic. I'm just trying to show you something very simple, and you'll see it here. And for some of you, this is too simplistic, and you're like, move on already. I get it. But for others, it probably will help. All right. So here's an instance where you have 2a on one side and a on the other. 2 minus 1 leaves 1a here. I've got 2b. So again, I went to that net equation. I looked what I had. Now I'm going to see if the sum makes sense. b plus b is 2b. Here's a c. I've got 1c here, 1c here, 1c here. So 2c's minus 1c is 1c on the product side. The d is right here, the e is right here, the f is right here. So the sum of these three equations here is equal to the net equation. So that means its delta H is equal to the sum of these three delta H's. That's what Hess's law says. Are you with me? All right. Sometimes it's not that simple. Sometimes one or more reactions must be reversed, which requires a change in sign for that delta H. Again, my approach is to look at the first reactant. The first reactant here is A. I see it right there, strongly suggesting that the first equation as written is fine. Further evidence of that comes from the B, and again I see it right there, suggesting that the first equation needs no alteration. Now I focus on this product C. It's over here. Well, the coefficient matches, but C is a product, and here it's a reactant. And that suggests to me that I need to flip this equation around so that C and D are products and E is a reactant. So all I did here was flip the equation around. But when I flip the equation around, I must change the sign of the delta H. Now the E's cancel, the A is here, the B is here, the C and the D are here. Delta H is the sum, because Hess's law says if the reactions sum together equal the net, then the delta H is the sum of the individual delta H's. but all I did was take the negative of the delta H2. Last piece. It says sometimes one or more reactions must be multiplied by some factor. It can be 2, 3, 4, 5, 6, 7, 8, 9, 10. It can be a fraction. Now I gave you a fraction as an example, but I do try and stay away from fractions at this level. They get very tedious. That requires that you multiply the delta H by the same factor. So again, piece by piece, first reactant A, right here, strongly suggesting that the first equation as written is fine. Second reactant B, it's a reactant here, coefficient's the same. Reaction 1 looks fine. But now I see, and I added to this, sorry I didn't take it away before you guys. Now I see 4C here. So we have to multiply this by some factor that will yield 4C. So what are we going to multiply this whole equation by? 2. So 2 times the whole shebang. And if we multiply that's stupid. If we multiply the equation as such, then what do we have to multiply this by? 2 as well. And that's actually what's shown here, but I distributed 2E, 2 times 2 is 4C, 2 times D. So the distributive property, just like in math. Now the 2E's cancel. A drops down, B, 4C, 2D. Hess's law says that delta H for the reaction is the sum of those two, and I, of course, multiplied that by 2 so that I had the correct number of products and that my intermediate canceled. Are you with me so far? Does it look awful? Nah. Sometimes you'll need to both reverse the sign and multiply by some factor, and we'll take a look at all types of examples here. We're going to walk through these 4 together, and then you're going to have a lot of time to practice and master Hess's law. Okay? So far, so good? Alrighty. So I've got this here. I'm going to work off my sheet. It says use the following equations to calculate the enthalpy change for the reaction. Indicate whether the reaction is endo or exothermic and justify your choice. I'm going to show you my approach. I'm going to make this a little bigger so you can see. And again, I like to just start at the beginning. 2 moles of nitrogen dioxide. Where is it? Find it.
In the product, the second equation.
Right here. Suggesting that the second equation must be flipped. So I'm going to make the product a reactant. And when I do that, what do I do to the sign on delta H2? I change it, I make it negative. Now, I've got this as a reactant. I've got dinitrogen tetroxide here and here, oh, that's a good sign that the first equation is okay. So when I sum these two equations together, I see that the nitrogen gas cancels, both coefficient of 1 on opposite sides of the two equations. Same thing with the 2 moles of oxygen gas. So the sum of these two equations is equal to the net. Hess's law says that I can sum their delta H's, and when I do so, I get negative 24.0 kilojoules. And so the reaction is exothermic because delta H of the reaction is negative. So hopefully the approach is clear. First reactant, find it. Does it match? If not, what do you need to do? We're going to work through a whole bunch together. And this, which really looks hard at the beginning, usually the kids like because it's very puzzle-like. I know it's Monday. Watching the Masters yesterday. All right. Number 2. I'm looking at the first reactant. Where is it? 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 Anybody with a pulse? Hannah.
On the reactant side of the first.
So it's on the correct side, but what's it missing? A 2. So should I just put a 2 here?
And you have to multiply the whole.
Good. And if I do 2's all across, I have to do what to this? You got it. Oxygen's all over the place. I don't want to play with oxygen yet. Carbon monoxide. Oh, that's over here. That's not where we want it. What are we going to do? Flip it. We've got 2 carbon dioxide. They're all gases, so I'm not going to bother with them. 2 carbon monoxide and oxygen gas. And that now aligns the carbon monoxide. And what can we cancel? Carbon dioxide goes bye-bye. We've got 2 O2 here and 1 O2 here. So 2 minus 1 is 1. So that's good. So now we just add them together. But I flipped this, so what should I have done to the sign? Make it positive, right? Negative times a negative is a positive. So we have 2 times negative 393.5 plus 566. And again, you're adding and multiplying and adding, so just keep your least number of decimal places is negative 221.0 kilojoules. And this is an exothermic reaction for the same reason we indicated above. It's not so bad. Alrighty, I've got propane. What should I do to the first equation? Leave it. Oxygen's all over the place, not playing. Here's carbon monoxide. It's over here. Uh-oh. What do we got to do? Multiply the second by 3 and flip it. I'm going to flip it first. I've got carbon dioxide, carbon monoxide, 1/2 O2. When I flip, I change the sign, but you said I also had to multiply by 3, right? 3, 3, and 3/2. And then I have to do what to this one? Multiply by 3. Good. And the water looks good. Let's see if the oxygen makes sense now. For the oxygen, I have 5 O2s here and 3/2 O2 here. Well, 5 is like 10/2 O2, right? And this is 3/2 O2, and they're on opposite sides of the equation. So I'm going to subtract them, and that's 7/2 O2, which is what I got here. Yep.
Can we pause for a sec? How come delta H of the second equation becomes positive?
Because we flipped the equation around. The carbon dioxide that was in the product went to the reactant in order to get the carbon monoxide into the product.
So when you flip it, change the sign?
Change the sign. And when you multiply it, you multiply it as well. Alrighty. So let's see if everything's canceling. We figured out the oxygen. The CO2's canceling. So now we get it to rip. That plus 3 times that. So we have negative 2219.9 plus 3 times 283, and that is negative 1,370.9 kilojoules, an exothermic reaction because delta H is negative, which is consistent with this combustion reaction, even though you only make carbon monoxide instead of carbon dioxide, probably because oxygen was in limiting supply.
What if you had the same substance, but it was in like a different state? If you had H2O, it was a gas, and H2O, and it was
You got to get them to cancel, otherwise there's a boo-boo
so
somewhere.
so it's like terms where
Yeah,
it's separate.
exactly. They both have to be X, if you will.
Okay.
That's a good question. This is Hess's law. Number 4 is a little trickier. I'll have you walk me through. Where should we start? Go ahead, Ethan. Where are we going to start? Start at the beginning.
Yeah, first one.
Where is it?
Like the multiply first equation doesn't have.
Why?
Because the coefficient in front of the final product isn't there.
Do we have to flip the first equation? Why not?
Because it stays in the same.
Because they're both reactants. So you are right. We're going to multiply this by 1/2, every one. And then we're going to multiply this by 1/2 as well. Okay. Now we've got 1 sodium bromide, which is here. Should we flip it? Nah. Should we multiply it? By what? So we've got 1/2, 1/2. 1/2 times 2 is 1. 1, 1/2, 1/2. And so we should multiply this by 1/2. Okay? Sodium chloride. Looks like we took care of that already. Half a mole of bromine liquid. That's right here. So are we done? Maybe, maybe not. Let's start to cancel things and see if they cancel. I have half a mole of calcium oxide, but I've got 1 mole of calcium oxide here. What does that suggest I need to do to the third equation? Multiply by a half. And you might have missed that if you didn't cancel everything out. So this goes with that. The chlorine gas is here. This is nowhere. Does this cancel? Sure, here and here. Is water in here? Nah. What does this cancel with? Good. And is there any, oops, we've got this guy. Does he cancel? Sure he does, right here. And now everything's either slashed or underlined. And how do we get the delta H of the reaction? Add them up. So you've got negative 110.9 times a half plus negative 60.2 times a half plus 65.1 times a half. Yeah. And you have negative 53.0 kilojoules. And that too is an exothermic reaction because delta H for the reaction is negative. Like I said, I usually don't play with halfies and thirds and all that. I think it's very, very tricky. But Hess's law says that if the sum of the reactions is equal to the net, then the delta H of the reaction is equal to the sum of the delta H's. Does that make sense? This is known as Hess's law. In your classwork, it's numbers 10 through 12. 12 is a little bit different, harder than anything I would give you, but still a good opportunity. In addition, there's a secondary classwork that I'm going to give you now. You want to do 1 through 4. The answers are on the back of the sheet, and if you want to see everything highlighted like I did in class, then I did post my highlighted key on Edline. This is not on tomorrow's quiz. Only delta H in regard to products minus reactants is. How do you feel about the delta H at this point? Like you just need some practice? All right. We have quite a bit of time in here before you start to move. I have a video. Do you want to watch it or do you want to maybe take a look at it at the end if you feel like you need it? At the end. All right, I think you did a really good job with Hess's law, but that video link is in your notes. So if you feel like you want a second look-see, it might be helpful. I don't think he did it with the A's and B's and stuff initially. I find that that usually sets the stage. But again, you should be able to complete all of this classwork before you walk out the door today. The quiz goes 1 through 9. We have 2 more lessons in this chapter for your class. They will be relatively short, and we've got a lab to look at for the end of the week.
Should we bring the classwork in tomorrow for you to check the grade or whatever?
No, we'll see how we're doing with it today. I'm going to hand out the Hess's law component. If you were out last week, you didn't get a table that you will need for the delta H determination of the first type, so make sure I get that to you. Any questions?
Are you giving us the equations to the quiz?
This is what I'll give you on the quiz. He said, are you going to give the equations? So I'm going to give you this. But I'm not going to give you products minus reactants for delta H because you need to remember that. We talked about the fact that you always go PP before you go running. It's products minus reactants. But I'll give you that if you think it'll be helpful. I'm not going to give you the steps on the calorimetry. You have to be able to do that. So make sure you've done enough. In addition, I want to think I can't remember. In your class, I can't remember if I gave you those extra problems Thursday or Friday. Remember, I wrote out those additional 4 problems? I just don't remember. I would think I did do it Friday because we had a lesson Thursday. So I figured if you wanted some initial practice, then these right here were some additional problems I gave you. I can make up an answer key where you can check off each other and then I can check yours if you feel like that'll be helpful. That'll be grossly similar to your quiz with the delta H calculation of the easy type that we talked about in our last class. All right, you're good? Yes? Success? Okay.